No, actually, could you switch it on?
Now can you hear me?
Yep, perfect.
Okay, perfect. Thank you everybody for coming out to my talk today. My name is Ciaran Regan. I'm from the University of Tsukuba in Japan, and today I'm going to be presenting my project titled Problem Solving in Language Model Networks. So I'm going to be talking about LLMs again. So there's been many techniques to improve the question answering performance of large language models. And many of those take inspiration from the way humans approach problem solving. So one example is reflection, where we pose a question to a large language model and it answers, and then it reflects on its response and tries to answer again. And this has been shown to improve the question answering performance in some tasks. Then another example is called React, where agents do reasoning and action steps in an interwoven fashion to improve the question answering performance. But it's worth pointing out that these methods only use a single agent. But collective intelligence, on the other hand, suggests that we can use multi-agent systems for more robust approaches. And there's been a few kind of approaches in this way as well. So one example was called multi-agent debate. The network looks a bit like this. So you have few agents which are all communicating with each other. And in this approach, agents first answer a question individually before they share their answer with all other agents. And then the agents answer again based on the responses of their neighbors. And this repeats for many rounds until a majority vote is taken as the final answer of the system. This has a few drawbacks. So for one, the input number of tokens grows quadratically with the number of agents. So because you have to aggregate all of the responses into a single prompt, it becomes very computationally expensive, and the full prompt won't fit into the context window. Also, the agents begin to lose focus when the prompt becomes very large. So this is a problem with this approach. Another attempt in a paper titled "More Agents is All You Need" was you just add more agents. But in this approach, it's scalable, but the agents aren't actually collaborating with each other. They're just answering individually, and then we take a majority vote in the entire system. And also, it's not clear what are the dynamics in these systems. So in a very A-life kind of fashion, I wanted to ask, what is going on in here? How are the agents actually talking to each other? Do they form a consensus? How do they influence each other? I wanted to kind of ask these questions in this work. So our contributions, we extend the concept of multi-agent debate to more complex networks. So not just looking at fully connected networks anymore. Then we examine the effect of different network structures on the question answering performance. So how about scale-free networks instead of fully connected networks, or random networks, for example? And then we analyze the dynamics. So we answer, how do the agents influence each other? Is there a consensus formed? And how does bias affect the results in these networks? So formally, we describe our network of language models as a multi-agent system, as graph G, with agents nodes A, a set of n debating agents, with edges connecting communication links between debate partners. And importantly, in this formulation, we include self-loops in the graphs, which indicates agent self-reflection. So it's the agent providing its own response back to itself. Then we build a system and we pose a question, and the agents engage in multiple rounds of debate before the majority vote is taken as before. And here I just give a quick example to show what this actually looks like in practice. So we pose a question from the MMLU dataset, a mathematics question. There's 4 possible options. In the first round, each agent answers individually. In the next round, they pass their response to all of their neighbors, and each agent answers again. And this continues for many rounds of debate. So we wanted to conduct an experiment to actually see which networks are the best and what are the dynamics that we observe. So we tested scale-free, random, fully connected, and fully disconnected networks, each with 25 agents for 4 rounds of debate, answering 100 questions from the high school mathematics dataset. And then we measure the QA performance and the influence, etc. And here we see the actual networks that were used in the experiments. So for the QA performance, we see on the graph here, it depicts the number of rounds on the x-axis and the accuracy on the y-axis. We see that first, of course, all agents get the same accuracy because they're not communicating with each other yet. Then in the second round, the accuracy spikes for all networks, which was expected. Then for fully connected networks in orange and random networks in purple, the accuracy kind of continues to grow before leveling off. And for fully disconnected networks, we find that the accuracy begins to decrease throughout the rounds. A really important result here was that the random networks actually perform better or comparable to the fully connected networks. And this result was really important because it uses significantly less input tokens. So it's actually around 250 times less input tokens. So it makes our inference a lot faster while maintaining the same accuracy as a fully connected network. And so we say that random networks outperform fully connected networks, both in accuracy and in cost. Then we wanted to analyze the influence. So the likelihood of an agent being correct based on its own response and the responses of the neighbor in the previous round. So in this graph, we see on the x-axis, the x-axis here is the proportion of neighbors that were correct in the previous round. So 0 here on the x-axis is the situation where an agent is surrounded by all incorrect neighbors, and 1 is when the agent is surrounded by all correct neighbors. And then the y-axis denotes the probability of the agent being correct in the subsequent round. Green denotes agents that were correct in the positive round, and red denotes agents that were incorrect in the positive round. And first, there's kind of two key takeaways. That collaboration is, of course, important. The probability of being correct increases as your proportion of neighbors that were correct increases, and also individuality. So an agent is more likely to answer correctly if they answered correctly in the previous round. So this is like the importance of self-reflection. And we get some interesting behavior if we analyze the edge cases in these systems. So when an agent is surrounded by incorrect neighbors, there's a 10% chance that they're going to switch spontaneously to the correct answer. And furthermore, there's a 30% chance that an agent with the correct answer will actually remain with the correct answer. So it's highlighting that self-reflection is really important in these systems. Then on the other side, when an agent is surrounded by correct agents, if they answer incorrectly, they're very likely to switch to the correct answer in the next round. So that is to say, collaboration is important. And then we analyze consensus in these systems. So the accuracy was interesting to discover the performance of these systems, but it doesn't reveal a lot about what's going on inside the network. In fact, a system can be correct with less than half of the agents actually giving the right answer. So here we show two examples. In one, we see all of the agents answered B, and in the other one, only 3 of the agents answered B. But due to the majority voting, these would both give the same answer as B. So to actually measure the level of consensus, we introduced the Simpson Diversity Index, which is given by lambda. Here, or is a set of all possible answers. So in the case of MMLU, there is 4 options, with one being like a mistake or a non-applicable answer. So that gives a total of 5. And PI is the proportion of agents that answered that answer I. So in MMLU, the total agreement corresponds to a Simpson index of 1, and a total disagreement corresponds to a Simpson index of 0.2. Then we split the questions into those answered correctly and incorrectly by the system. And we found that when the system is in full agreement, it's very likely that it answered correctly. So full consensus is associated with correct answers. On the other hand, split consensus is associated with both correct and incorrect answers. But this result is kind of suggesting that we can use the Simpson Diversity Index as a measure of confidence in the system. Then finally discussing bias. How would biased agents influence the collective? So to analyze this, we inserted correct and incorrect answers into the system. So in particular, we took scale-free networks and manually instructed them to either answer correctly or incorrectly and provide their reasoning response. And then we carried out the same analysis. And the results are shown here. So the topmost green line is the bias, the correct answer inserted into the hub of the scale-free network, and the lowest line is the incorrect answer inserted into the hub of the scale-free network. And what we find is inserting these biases into the hubs has a significant impact in the overall performance of the system. But inserting the bias into the edges of a scale-free network has very little impact. So it just shows that kind of the placement is quite important. And it suggests that what happens if we were to put smarter models, larger models into central hubs? Could we design a topology that performs better? So this is kind of a question for our future research. So to conclude, collective intelligence is a promising approach to improving the performance of large language models. Random networks can outperform fully connected networks in both cost and QA accuracy. So network topology is quite important, we believe. And then in these collective intelligence-based approaches, we can use metrics such as the Simpson Diversity Index as a measure of confidence in our answers. In future research, we're going to explore the effects of dynamic network topologies. So we heard in the other talks that dynamic networks can be quite beneficial, so I'd like to explore that more. I'd like to analyze using a mixture of models. So we just used GPT 3.5, I believe, but I would like to try switching different models in the network and then increasing the number of rounds and agents to see what kind of behaviors we observe. Then finally, I want to mention that our code is fully available here. And also we've built a demo. So if anyone wants to go to this website, you can actually construct different networks and ask questions to the agents. Not only can you get a summary of how the agents answered, but you can actually chat directly with the agents and see, why did you answer that? What were you thinking? Why did you change your mind? So you can actually interact on a collective level and an individual level. So with that, I want to thank my supervisor, Professor Mizukioka. I'd like to thank my collaborator, Alexander, and thank you all for listening.